If you have worked with Spring Boot, you have probably used Redis before. You add a couple of dependencies, configure the Redis connection, annotate a method with @cacheable, and suddenly your API becomes much faster. Most developers stop there, but have you ever wondered what actually happens after you add that annotation? How does Redis find data so quickly? Why doesn't it become slower when it stores millions of keys? How does Redis know when to remove old data? What happens if the memory becomes full? And how do large-scale applications prevent thousands of users from hitting the database at exactly the same time? These are the questions that separate someone who uses Redis from someone who understands Redis. In this video, we will open the Redis black box and explore everything happening behind the scenes. By the end of this video, you will understand how Redis stores data, why it is incredibly fast, how Spring Boot integrates with it, and the production patterns used to build reliable high-performance applications. Before we understand why Redis is fast, we first need to understand how it stores data. Unlike traditional relational databases, Redis stores its data in memory, also known as RAM. Reading data from memory is much faster than reading it from a disk. That is the first reason Redis is so fast. But storing data in memory alone is not enough. Redis also stores data using specialized data structures. Instead of storing only rows and columns, Redis supports several different types of data structures, each designed for specific use cases. The most commonly used data structures are string, hash, list, set, sorted set, stream. In Spring Boot applications, when we use Redis as a cache, the most common data type is a string. Even if your application returns a Java object, Spring Boot serializes that object into JSON and stores it as a string value inside Redis. Now let's look at how one cache entry is stored. Every cache entry contains three important pieces of information. The first is the key. The key uniquely identifies the cached data. The second is the metadata. Metadata stores information such as expiration time, serialization details, and internal bookkeeping. Finally, we have the value. The value contains the actual business data that our application needs. For example, imagine a user requests all electronic products. Spring Boot might generate a cache key like this. The value associated with that key is the JSON response containing the product list. Every cached object in Redis follows the same pattern. Once you understand this structure, the rest of Redis becomes much easier to understand. Now that we understand how Redis stores data, let's answer the biggest question: why is Redis so fast? Many developers assume Redis searches every key until it finds the correct one. Fortunately, that's not how Redis works. Imagine Redis stores 10 million keys. If it searched each key one by one, every lookup would become slower as more data was added. Instead, Redis uses a hash table. When your application requests a key, Redis first passes that key through a hash function. A hash function converts the key into a numeric value. That numeric value tells Redis exactly which bucket contains the data. Instead of searching millions of keys, Redis jumps directly to the correct bucket. It then retrieves the value almost instantly. This process gives Redis an average lookup time of O of 1, also called constant time. Whether Redis stores 1000 keys or 10 million keys, the lookup process remains nearly the same. This efficient lookup mechanism is one of the primary reasons Redis can deliver responses in microseconds. Now that we understand how Redis stores data and how it performs lightning fast lookups, let's see what actually happens when a request reaches your application. Imagine a client sends a request to fetch all electronic products. The request first reaches your Spring Boot application. Instead of immediately querying the database, Spring Boot first checks Redis. It generates a cache key and asks Redis, do you already have this data? From here, two scenarios are possible. The first scenario is called a cache hit. A cache hit means Redis already contains the requested data. Redis immediately returns the cached value. The application skips the database completely and sends the response back to the client. This is the ideal scenario because it reduces response time and protects the database from unnecessary queries. Now let's look at the second scenario. Suppose Redis doesn't contain the requested data. This is called a cache miss. Since Redis cannot return the value, Spring Boot executes the business logic and queries the database. Once the database returns the result, Spring Boot stores that result in Redis using the generated cache key. Finally, the response is sent back to the client. Now if another user requests the same data, Redis already contains the value. The second request becomes a cache hit and the database is skipped. This is simple mechanism is the foundation of every caching system. The first request builds the cache, every subsequent request reuses it. At this point, you might have an important question. If Redis stores data forever, how does it stay up to date? Imagine a product price changes in the database. If Redis keeps the old value forever, users will continue seeing outdated information. To solve this problem, Redis provides a feature called time to live, commonly known as TTL. TTL defines how long a cache entry should remain valid. When a key is created, Redis starts a countdown timer. As long as the timer has not expired, Redis continues serving the cached value. Once the timer reaches 0, the key expires. The next request becomes a cache miss. Spring Boot reads the latest data from the database, stores a fresh copy in Redis, and the TTL countdown starts again. TTL helps maintain a balance between performance and data freshness. A longer TTL reduces database traffic but increases the possibility of stale data. A shorter TTL keeps the data fresher but increases database access. Choosing the right TTL depends on how frequently the data changes. There is another important detail that many developers don't know. Redis removes expired keys using two mechanisms. The first is passive expiration. When an application requests a key, Redis checks whether it has expired. If it has, Redis removes the key immediately and behaves as if it never existed. The second mechanism is active expiration. Redis continuously scans a small number of keys in the background and proactively removes expired entries. These two mechanisms work together to keep memory clean without impacting performance. Redis is an in-memory database. That means every cache entry consumes RAM. Unlike disk storage, memory is limited. So what happens when Redis runs out of memory? Redis does not automatically increases its memory. Instead, it follows an eviction policy. An eviction policy decides which cache entries should be removed to make room for new data. The most commonly used policy is least recently used, or we can call it as LRU. The idea is simple. If a cache entry has not been used for a long time, it is less likely to be needed again. Redis removes that old entry and stores the new one. Imagine your cache can store only 4 products. Users continuously request products A, B, C and D. After some time, product A is no longer accessed. Now a request for product E arrives. Since the cache is full, Redis removes product A and stores product E. This makes room for new data while keeping frequently accessed data available. Besides LRU, Redis also supports other eviction strategies such as LFU, random and TTL based policies. However, LRU is one of the most widely used policies for application caching. So far, we have learned how Redis stores data, performs lightning fast lookups, manages expiration using TTL, and frees memory through eviction. Everything works perfectly until the cache expires. Let's imagine our application is serving thousands of users. All product information is already cached in Redis. Every request becomes a cache hit. The database is almost idle. Life is good. Now imagine the TTL reaches 0. Redis removes the cache entry. This is completely normal. If only one user requests the data after expiration, the application simply reads the database and rebuilds the cache, and everything continues as expected. But production systems rarely have just one user. Imagine 1000 users refresh the page at the exact same moment. The first request checks Redis. The key doesn't exist, so it queries the database. A few milliseconds later, the second request also checks Redis. The cache is still empty because the first request has not finished rebuilding it. So the second request also queries the database, and the third request does the same, then fourth, then 100 more. None of these requests know that another request is already rebuilding the cache. Every request independently decides the cache is empty, so every request hits the database. Instead of one database query, your application suddenly generates 1000 identical database queries. This is called a cache stampede. A cache stampede can overload your database, increase response times, and in extreme cases, cause service outages. So the obvious question is, can we allow only one request to rebuild the cache? Yes, that's exactly what a distributed lock does. Notice what happened. The problem is not Redis. The problem is that every request tries to rebuild the same cache. So instead of reducing database traffic, Redis accidentally causes a database spike. Now let's solve it. The first request acquires the distributed lock. Only that request is allowed to query the database. Every other request waits for a short time. Once the first request stores fresh data in Redis, it releases the lock. Now all waiting requests read the newly cached data from the Redis. Instead of 1000 database queries, we execute only one. This simple coordination mechanism protects the database during traffic spikes. Let's understand this code. First we check Redis. If the data already exists, we immediately return it. If Redis doesn't contain the data, we acquire a distributed lock using the cache key. Notice that every request for the same product competes for the same lock. Only one request succeeds. That request queries the database, stores the result in Redis, and finally releases the lock. Every waiting request now reads the cached value instead of hitting the database again. Now that we understand how Redis works internally, let's build a complete Spring Boot caching application. We will start by adding the required dependencies. The cache starter enables Spring's caching abstraction. The Redis starter provides connectivity between Spring Boot and the Redis server. Next, we enable caching. Without the enable caching annotation, Spring Boot completely ignores annotations such as @cacheable and @cache-evict. Now let's configure Redis. Here we configure the Redis connection and defined Redis as the cache provider. We also configure a default TTL of 5 minutes. Next, let's customize how values are stored. This configuration defines the default TTL, disables caching null values, and stores Java objects as JSON. Now let's use caching in our service. This single annotation performs everything we have learned in this video. Spring Boot generates the cache key, checks Redis, returns a cache hit immediately if the data exists. Otherwise, it executes the method, stores the result in Redis, and applies the configured TTL. Let's also see how to remove stale cache entries. Whenever product data changes, we should remove the old cache entry. The next request automatically rebuilds the cache using the latest data from the database. This keeps Redis synchronized with the source of truth. We have learned how Redis works internally and how to integrate it with Spring Boot. Let's finish with a few production best practices. Not every piece of data should be cached. Cache data that is read frequently but changes infrequently. Examples include product catalogs, application configuration, user permissions, and search results. Avoid caching data that changes every second, such as payment status, account balances, or OTP validations. Choose TTL based on your business requirements. Static data can have a longer TTL. Highly dynamic data should use a shorter TTL or sometimes should not be cached at all. Finally, always monitor your cache hit ratio. A low cache hit ratio may indicate that your TTL is too short or your cache keys are not designed effectively. Redis is a powerful tool, but its effectiveness depends on thoughtful cache design. When used correctly, it reduces database load, improves response times, and helps applications scale efficiently. In this video, we went beyond simply using Redis. We explored how it works internally. You learn how Redis stores data, performs fast hash-based lookups, handles cache hits and cache misses, manages data expiration with TTL, frees memory through eviction, prevents cache stampedes with distributed locks, and integrates seamlessly with Spring Boot. The next time you add add cacheable to your code, you will know exactly what's happening behind the scenes and why it makes your application faster. If you found this video helpful, consider subscribing to GK TechVerse.